Yeah, ready to go.
All right, so let's get started. This is our first lecture. Juan Maldacena is here. We're very glad to have him. He's been here 2015, 2017, now 2019, always giving great lectures, and this year he's going to talk about large N.
Okay, so I was asked by the organizers to give a general talks about large N, and this is an old subject. So in large N has been applied to quantum field theory, to the analysis of quantum field theory for a long time, and there are different examples, and we'll try to go through the different examples and point out the differences, similarities between different examples. Now, why do we consider large N? Well, first of all, large N is a simplification. So N is roughly the number of fields. It could be the rank of a gauge group. It could be the rank of a global symmetry. It could be some, but roughly speaking is the number of fields. So field theories with large numbers of fields sometimes can be simpler. And so it's simple, but nevertheless it retains some of the interesting aspects of quantum field theory, such as non-trivial renormalization. We'll see phenomena like something similar to confinement, or more precisely the generation of a mass gap in certain simple models, the emergence of gauge fields. And so those are things that can be solved exactly thanks to large N. Now, in addition, there are some theories that appear in nature, which are essentially large N theories. So one example is the theory of BCS superconductivity, for which the reason it is solvable is because the diagrams that appear are essentially the same diagrams that appear in ON vector models. So the reason that theory is solvable is similar for the reason that large N vector models are solvable. And another reason is that some interesting theories like quantum chromodynamics, even though N is equal to 3, have a phenomenology or have some behavior that suggests that is somewhat similar to the large N version. So perhaps solving the large N version of QCD might be somewhat close to QCD. So there are theories in nature where large N might be a good approximation. Now, of course, large N really goes way back. I mean, it's just thermodynamics is related to large numbers of particles, for example. And this is one of the rare subjects where social scientists were actually ahead of us. So there were people working computing statistics, so numbers for the state. That's where the word comes from, at least. And then people apply those, and they noticed that there were some regularities, like the number of births between female and male. You can't say in a particular birth, but you can say statistically what the ratio should be. Number of criminals born, similar. There were patterns that remain over long times. And so this then was, of course, applied to physics, and we now know that thermodynamics comes from statistical mechanics, and you can derive it in this way. And of course, that was the subject of a couple of centuries ago. And now we're trying to understand one of the motivations for large N is also trying to understand how space-time appears from quantum mechanics. And one framework is the idea that, again, there is some kind of large N limit involved. And so that's one other motivation for studying large N. So the plan for these lectures is that we'll start with vector models, which is the simplest kind of large N limit that in the context of quantum field theories. Then we'll go to the SYK model, which is sort of the next to simplest, and it's very similar to the large N vector model, and that's also similar to the tensor large N limit, where there is a special simple class of diagrams that dominates. And finally, we'll discuss some aspects of the matrix large N, which has to do with large N gauge theories. Okay, so let's start with the vector large N. Most of what I will say, it's very nicely explained in Polyakov's book. So if you want an expansion bigger than longer than my discussion, you can find it in Polyakov's book. So let's start with vector large N limit. So we have Now, I should say that, well, I would like to hear some feedback from you of whether these are the kinds of things you would like to hear, or you prefer me to go faster or slower. Okay. Okay, so the vector Larsen appears when we have a field that has one index, and sometimes this is the index that is in an ON representation. So it's you could think of this as an ON index. So a simple example, we'll discuss various examples just to keep the discussion concrete, but these discussions apply to a large number of cases. So imagine you have a simple 5 to the 4 theory, so in any number of dimensions in principle. So which has the usual Lagrangian. It's a 5 to the 4 theory with an ON global symmetry. Okay, so that's the context. Now, one motivation to study this theory is that the particular case of d equal to 3 and n equal to 1 and n equal to 2 are important for describing some aspects of nature. So the n equal to 1 is the Ising model, which discusses the critical point in, let's say, liquid vapor phase transitions and so on. And the n equal to 2 is what describes the similar transitions when we have a order parameter which is a phase. It has a phase. It's complex, like the superfluid transition, for example. Okay, so those are interesting cases, and of course, here in this case, the large n would be an approximation. So it would be you take large n and then maybe expanding 1 over n, and you might try to, in that way, get an approximation to the interesting cases. Or you might say, well, I just want to understand all of them. N equal to infinity is a simple one. So there are a couple of ways to think about this theory. So one will be in terms of the functional integral, which we'll discuss later. And the other one will be in terms of the diagrams that we'll discuss right now. So we'll see that in these kinds of theories, there are special kinds of diagrams, which are the diagrams that dominate. So let's first consider the diagrams for the propagator. So we'll denote the propagator by G. And so we have the free propagator. And then we have a correction that comes from a diagram like this. So here it's a propagator. There are the indices of the field. So we have the I and I index here. And then here we have a loop of some other index, k. And so this contributes with a factor which is g squared n. Right? So that's this diagram. And then there are a bunch of other diagrams that you could obtain by simply essentially iterating this diagram, right? So on this line, we could add this. So now on this line, we could add a similar loop. We could add, of course, the loop on this line. We could add on all lines that appears, we could add this loop. And all those diagrams, for the same reason, will be powers of g squared n. So these are diagrams that look like this. So which come from iterating those diagrams. Of course, we could also have this structure repeat. And these are called cactus diagrams, right? Looks like a cactus. Okay. We'll have lots of plant biology here. Now, of course, these are not all the diagrams. There are non-cactus diagrams. So, for example, at second order in G, we could have a diagram which has this form. And so here we have the index I. So here the index I has to appear in one of these lines. And we had also the index line over there. And then we have some index L here. So we have two G's. Yeah, so we have two G squares, because remember the fourth order coupling had a G squared. So we have G squared to the fourth, but only one power of n, right? So this diagram is down by a power of n compared to all these other diagrams that are of the form G squared to some power k, okay? So, well, k. So here in this case there are 1, 2, 3, 4 index loops. It's G to the fourth. So in the limit that n goes to infinity and G goes to 0, keeping G squared n fixed, right? then we keep all these diagrams, all the cactus diagrams, but we don't have the non-cactus diagram. So this is a non-cactus. Okay, good. Now, in these cases, we can, when the diagrams are relatively simple, we can sum them all. So we can sum the diagrams by writing down some equations. And so you can write an equation for G as a sum of just a line with no with nothing, and then a line with here some cactus which cannot be broken into a single line, and then these are called the one particle irreducible diagrams, and then you can have this and so on. This you can do for any field theory. You can have this expansion, and this expansion just gives 1 over d squared minus m minus sigma. Okay, this is sometimes called the self-inertia. So for any theory, you can write the propagator this way. Now, so here sigma would be something that in momentum space would depend on momentum. Okay, and what's special about this theories is that you can write an equation for sigma. So you can write sigma equal, and what was the sigma? So sigma was basically you have an interaction and then 2 lines that come out, and then here you can have insertions of many other things. So the sigma is really it contains a g squared and n and basically the g again. So all the diagrams that sum up to g. So we could call this whole sum of diagrams the full propagator, right? All the sum of all the diagrams, and that's what we get in sigma. Okay, or equivalently, we have g squared n, and then we have g of x comma x. Okay, so we have g, but g on coincident points. Okay, because the interaction was local.
And your sums propagated there, do you want m squared?
M?
Second line.
Yes, m squared. Right, so in momentum space we would write sigma equal to g squared n, and then integral, let's say, d squared q. So, well, the d to the d, this is in any dimension of the momentum propagating here, and then this is 1. This is q squared plus m squared minus sigma of q. Okay. Now, you see that so this is sigma of k. So k is the momentum flowing through sigma, but the momentum here is just q, and k doesn't appear here, so sigma will be in all cases independent of k. Okay. So sigma is just a constant. So that's an additional simplification we have in this case, where we have this translation symmetry, and so. So all that happens in these theories with the propagator is that we have some correction to the mass. That's all. Okay, that's just for the propagator. We'll see later some more interesting effects. Now, naively, you might think that this shift in the mass is somehow trivial. You just the mass finite would be finite or infinite mass renormalization, but it's not so trivial because this could be, for example, a finite temperature field theory, right? And then at finite temperature, you would have a shift in the mass which depends on the temperature. So what you are allowed to subtract from the bare mass is any constant, but not something that is temperature dependent. And in fact, these equations contain the thermal mass that is generated by the interaction with the backgrounds and so on when you consider this theory at finite temperature. And for this reason, when you find the solution and then you could go back and evaluate the action, we'll see later a simpler way to think about that. You can calculate, for example, the free energy as a function of the temperature for this theory, which is non-trivial. Okay. Good. So that's one thing. But let's continue analyzing this theory. So most of what we say about large n, all this counting discussion, is independent of the dimension. Okay, so only the structure of the theory matters. But for some of the details of the physics that we're going to analyze, we'll have to choose some special dimensions. But that's just to connect it to special theories. The analysis could be done in other dimensions, and the details would be different. So we're going to consider the case d equal to 3 now. So we set dimension equal to 3, which we said was one of the interesting cases. And we are going to fine-tune the bare mass so that m squared minus sigma is equal to 0. Okay? So we are at 0 temperature. We tune the mass in such a way that this equation is obeyed, and so on. And then that implies that phi is massless, right? It's effectively, well, it's really massless, and the 2-point function of phi, phi I with the same index I, will go like 1 over x. So this is the solution. This is just the usual inverse Laplacian in 3 dimensions, 1 over r. And this should be compared to what we find for an operator of general dimension delta. This is the general formula, and this implies the dimension is 1/2. Are you familiar with this definition of dimension? I assume you might have seen it before many times. Okay. So now, okay, so that's good. So that looks pretty trivial. So it looks like phi is just basically a free field. Okay. So that's the dimension of what's sometimes called the spin operator in this. Well, in the Ising model would be the spin operator. The Larsen version of the dimension is 1/2. So we just computed it. So look a little trivial. So now let's consider something else. Let's consider the operator phi squared, right? So this is a composite operator. So O is now O of x is phi squared of x. So that's the operator. And so now in the free theory, if phi was actually free, we would have just this diagram. Essentially, in position space, this is trivial. It's just the square of this. And therefore, the dimension would be 1. So delta free would be 1. Okay, is 1. But now let's evaluate the same thing in momentum space. So there is some momentum flowing through the diagram. Let's call that k. So we're going to compute, let's say, O minus k, OK. And this is equal to, well, now we write the same thing in Fourier space. So q squared k minus q squared, right? And, well, what is this? So this is some integral. It's a convergent integral, so it has no infrared divergences or UV divergences. And the result can be determined by dimensional analysis. So the only thing that appears here is k. So this whole thing goes like 1 over k. Okay. And of course, the Fourier transform of this gives us 1 over x squared, okay, which was the free result. Okay, so we went through this in detail. Let me call, so this is the free answer, free, and let me call this A. Okay, so A is the free answer. And now we would like to understand the interacting answer. And so we had the free diagram, and now we can add some other diagrams like this one. Okay. Here we could add all the cactus correction, right? But the cactus corrections don't do anything. They just keep the mass equal to 0. So I'm not going to draw them. But these lines represent the full propagators. Okay. So that's the next correction. And in this same way, one can check that all the leading order diagrams in large N are a sequence of bubbles like this. So we have kind of bubble diagrams of this form. So these diagrams roughly look like as if a particle is propagating. So if you think of a particle as made of these bubbles, it's basically like a particle that propagates between the two. But anyway, so we can sum all these diagrams, and the result is very simple. This is just a geometric series. So the first thing was A, and the result of this diagram is, well, there is a factor of g squared n, and then each diagram individually will give you A. So it's a geometric sum, which is 1 minus g squared n times A. Okay? So that's the answer. So here you see the simplicity of these large N limits. We can just compute this, and it's not equal to the free theory. Okay? It's not equal. It's a non-trivial function of k. It will be different at the short distances and long distances. And so let's compute the long distance answer. So we're interested. Yeah, I should have said this. So we are in d equal to 3. So this field phi has dimension 1/2, which has computed in the free theory. This interaction has dimension 2, and so this G has dimension 1, so it's a relevant perturbation. And the theory is free, of course, in the ultraviolet and becomes interacting in the infrared, and becomes some interacting conformal field theory in the infrared. That's the so-called Wilson-Fisher fixed point. Please.
So if you had another bubble that's touching the two simultaneously, does that die in the margin?
Yes, yes. Yeah, exercises check that this is not the correction. Yeah. Yeah, that's again a kind of non-cactus correction. Yeah. Okay. Good. So now we have the answer, and we can go to low energies, and where the interactions become important. And indeed, when we go to low energies, A becomes large, so K becomes small, and A becomes large. And this term becomes more and more important and corrects the answer. And it gives that this function goes like a constant, right? Independent of K at small k. So that looks at first a little weird. So we had this constant. But if you have a constant in Fourier space, that means when you do the Fourier transformation, that will give you a delta function in position space. Now, probably from previous lectures, you heard that these contact terms or short distance singularities are not important. So we're interested in the conformal field theory. In the infrared, we're interested in the operators at different positions. Okay, so this constant term is not important. Okay, we want the non-constant correction. So we want to find the piece that depends on k, and well, we can do it in various ways. So we can expand this to next order in k for small k, or we could say that we add and subtract. Anyway, so you understand what I mean. So so when you do that, so you get the constant, and then by expanding to next order in this 1/a expansion, so you get d squared times 1/a. Okay, and then this goes like 1/g squared n squared times k. Okay, so that's the final expression for the correlator. If you do it correctly, there's a minus sign. And the Fourier transform of this, so to do Fourier transforms, remember we are doing d3k of whatever appears here is k, e to the I kx. And so we just do dimensional analysis, so there are 4 powers of k, so there should be 4 powers of x here in the denominator. So we have 1/x to the 4th, and therefore the dimension of the operator phi squared, so delta of phi squared, now in the interacting theory, in the Wilson-Fisher, Large Wilson-Fisher fixed point, is 2. Okay, so it was 1 in the free theory, but it's 2 in this non-trivial, interacting theory. Okay, so it's non-trivial but simple to solve. By non-trivial, I mean not the Gaussian theory, not the free field theory. Okay, so that's those are the dimensions we have, and then one can compute 1/n corrections by for discussing 1/n corrections is a little bit, well, you can do it with the diagrams, including the simplest diagrams that, for example, the one you mentioned, you can also do it using the path integral. So there are some techniques to compute the 1/n corrections. You can compute them, and then you can compare to other things like the bootstrap and so on. Okay, so now we'll start discussing the same theory. So we'll come back to this action, but instead of talking about these diagrams, we'll talk about the we'll do a path integral derivation of basically the same things, and it's useful to have these 2 points of view. So now we have C, which is the integral d phi of this action, and we're going to write that integral by introducing another integration variable, which we're going to call sigma tilde. It's kind of going to be close to sigma, where we have an action which is minus, so we write we have the integral d phi squared plus m squared phi squared minus sigma tilde phi squared minus sigma tilde square over 1 over g squared. Okay. So this action has the property that if we first integrate out sigma, we get the original action. But we now have the option of integrating out phi, where now it appears quadratically, and that's the reason we did this change of variables. And if we do that, then we'll get an action which involves only the integral over sigma tilde, and an action which only depends on sigma. So it's e to the minus n, so there is an overall factor of n. And then we have 1/2 of the log of the determinant of this operator, minus d phi squared plus m squared minus sigma tilde, minus 1 over g squared n times this factor. Okay, so the n here appear because we pulled out an overall factor of n. But now the important aspect of this action is that before the number of integration variables depended on n, but now we have the integral of just one variable, and n is appearing only as a parameter in the action. And it's an interesting parameter because it's just multiplying the whole action. So it's basically like 1 over h bar for this action. So if we should think of chi tilde as a quantum field, n is the 1 over h bar of that field. So in the Larsen limit, this field chi tilde becomes classical. Okay. Now this is not quite a local action, so this you should not take this idea that this is a quantum field. Well, it depends on what you mean by quantum field. It's certainly an integral. It's a variable in the functional integral, so in that sense it's a quantum field. And whether it's associated to a particle or not depends on the properties of this determinant and the kind of solutions we are going to look at. Okay, so you have this action, and since we are in the classical limit, you can compute the classical equations for sigma tilde. Okay, so you take the functional derivative with respect to sigma tilde, and the classical equations you obtain are precisely the equations that you have here, right? So you'll get this equation here. Okay, so that's the equation for sigma tilde, and sigma is the solution of the classical equation. Okay, so that's why I sort of use different variables. But essentially, sigma tilde is equal to sigma. Okay, so that's so the classical solution for here for this just essentially solves these equations, and then if you were to calculate the small fluctuations for sigma around this action and calculate the propagator for sigma, then that's what we did here when we were calculating when we were summing this geometric series. Okay, so this is essentially the propagator for sigma. Okay. Now, sigma is therefore associated to the operator essentially phi squared, and it was important to keep sigma because phi squared was the operator here that was appearing in the action. You could extend to a larger number of operators, so operators with spin and so on, and introduce extra fields. And so you would get a theory which has many fields of different spins. And there are various ways in which people have tried to analyze this. And you are supposed to get a theory. Okay, so you get something this way. And there is a conjecture that whatever you get that way should be the same as another theory that was independently defined, which is called the Vasiliev theory. I won't enter into details, but it's a theory of gravity in 4 dimensions with higher spin particles. And it's a complicated theory. And that's supposed to be equal to what you would get by including operators also of the form phi, many derivatives of phi. Okay. Okay. So we won't discuss that in detail. I just mention it as a curiosity. We'll now go to our next example. So the next example of an interesting phenomenon you can study using large n. So now we are going to discuss a few applications. So the rest of this talk will be a few applications of this large n limit, okay, large n vector models. So now we'll set d equal to 2, and we consider the Sn model. So a model with a target space which is a sphere of dimensions n minus 1. So we have an action of this form. Well, we are going to write it like this: phi squared minus 1. Okay. So this is a Lagrange multiplier that implies that all these fields phi lie on a sphere, and then this is the just ordinary kinetic term. If we first integrate this out, then here we get an action for fields whose target space is a sphere. Okay. Now we are in 2 dimensions, and in 2 dimensions the field phi is dimensionless, and therefore and this action is classically conformal invariant, scale invariant and conformal invariant, so G has no dimensions. Okay, so that's the theory classically. Now quantum mechanically the theory will develop a beta function and so on. You can in principle calculate, and we'll actually calculate it. And what we are going to show is that the theory develops a mass gap in the infrared. We are going to be able to solve the strong dynamics that this theory has in the infrared. Okay? And large N will be useful for that. So we do the same trick as before. So it's almost identical to what we had over there. So we first integrate out phi. We get an action. So now after integrating out phi, so int out phi, we get an action for sigma tilde, which is again has the an overall n minus minus 1/2 log of the determinant, etc. The same thing. The only difference is that instead of a phi square here, we just have a phi. Okay? Instead of a sigma square, we have a sigma that comes from this term here. Okay, that's all the difference. And therefore, when we calculate the equations of motion, we get an equation which is very similar to the equation we had before, and the only difference is that sigma will not appear in the right-hand side. So we get 1 over g square n. So before we had a sigma here multiplying, and then we'll have an integral d square q over q squared minus sigma. So here we had no mass initially, and so we had just this term, right? So before we had this equal to sigma, and before we were putting the g square n in the other side, but that's the only difference. So we can now, again, due to translation, again we say sigma is, let's say, constant as a function of q, and then we do this integral, and the integral, well, we put the pi's and so on. Even with the pi's, you can show it's equal to log of lambda squared over minus sigma squared, minus sigma tilde. Well, sigma now will be the classical solution, so I'm not going to drop the sigma tilde. So it's a UV divergent, and of course we expected some UV divergence and some logs because we said there would be a beta function. And we can rewrite this equation, so noticing that this would be an effective mass for these fields. So we can write m squared equal to minus sigma, so this is just the definition of m squared, equal to e equal to lambda squared. We just exponentiate this formula, e to the minus 4 pi over g squared n. Okay. So this g is the bare coupling. Okay. So the coupling at scale lambda, or maybe we could call it g sub lambda. Okay. So now when lambda goes to infinity, so when we remove the cutoff, we want to keep the infrared constants fixed, so the mass square would remain fixed, and that would force us to take g squared to 0. Yes?
So in the example there,
Yeah.
is equal to 3, you could have also a term that goes like y to the power of 6, right? Because
Yes. You could. Yeah.
For the, can you repeat the question?
Yeah. So sure. the question was, here for d equal to 3, could we put in a factor phi to the 6? That's marginal. The theory is still at least power counting renormalizable, right? And you could put it. Yes, you can, and you can analyze that theory also. People have also analyzed that theory.
So in the infrared, it's a pretty
Well, if you just put the phi square, the phi to the 6 here, and you flow to the infrared, so this one will be more important, but depends on the details of the coefficient. But this one will typically be more important and will dominate the physics and will have what we discussed here. But one could analyze it in detail and tune the coefficients. This one to be very small, the other one larger, and you have various physics. And I don't remember all the possibilities, but people have discussed this too. Yeah, you can do many things. I'm not exhausting the list of things that can be done. I'm just giving you a little sampler of things that can be done, illustrating sort of different physics. Previously, my main point was to illustrate the appearance of an anomalous dimension. Right now, my main point is the appearance of a mass gap for a theory. So we had a theory that initially had massless particles, and naively there is no way to give these particles a mass, keeping all the symmetries of the sphere, right? But nevertheless, the quantum dynamics generates an effective mass scale. It's not a mass for the original particles. Notice there is a second phenomenon that happens here, which is the following. So if we want to analyze this theory at high energies, we would, or at least classically, we would choose a web for the field phi, and then we quantize around that value of phi. So we pick a point on the sphere, and then we have small fluctuations. We have massless particles, so classically we have massless particles, but that transform in On minus 1, not On. Okay. While in the infrared, so at high energies, or classically, the On symmetry was broken to On minus 1. So this is classically, right? But quantum, what happens is that the On symmetry is restored. So we have really full symmetry On. So these massive particles that we have here are these massive fields phi, which are transformed in the vector representation of On. We have restored completely the symmetry. So these are two phenomena that this theory displays, and this is sometimes viewed as a toy model for QCD, in the sense that in QCD also we have asymptotic freedom and the generation of a mass gap and dimensional transmutation. Okay, and initially the gluons are massless, but then we develop a mass gap. So this was historically important for understanding that those are phenomena that can happen in quantum field theory. And this is perhaps the simplest example where this phenomenon happens. Okay, so that's another phenomenon. So now we'll complicate the target manifold slightly. So we'll start with a bunch of complex fields. So we'll have n complex fields. Let me call these complex fields Ci. Okay. Let me call them Cj. So we'll continue to impose the condition that sum over all these fields squared is equal to 1. Okay. So at this point we just have a sphere the same as what we had before. But now we are going to remove the overall phase of all these complex fields. So we're going to make an identification that Cj should be identified with e to the I alpha Cj. Okay, where this alpha is the same for all j's. Okay, so we'll remove the overall phase of the fields, and that space of the space of C's with this constraint and the phase removed is called the CP complex projective space of dimension n-1. Okay, that's just the name for this space. So we can write an action. So we can write down a metric in this space, and a simple metric on this space is the following. So take some coordinates where you have basically a sphere, and then pick one of the angles of the sphere to be this the overall phase, okay, and then just write the metric and then remove just this term that has the angle. Okay, so that's called the Fubini study metric. And anyway, that's just the name. But one other way of doing the same thing is to subtract this phase by introducing an auxiliary gauge field. So we have the alpha, A alpha Cj. I'm probably writing too small, right? Okay. I'll try to remember. Wait, please shout if I write too small, okay? Because even I find this indice small. Okay, so we have what we have done is we have introduced the gauge field that gauges this U1 symmetry corresponding to alpha. Okay. If we do what we were saying about writing the metric for alpha, so we would have a term like this. We would have a term like this in the metric. This is just without the gauge field. What we want to do is remove the alpha. So, but after we do that, so B depends on the other coordinates that we have introduced. So here now we will have an A alpha. And so now you see that by integrating out over alpha, this is just a Gaussian integral, and just we remove this whole term in the action. And that's what gives us the so-called Fubini study metric. So this is the procedure that removes this. So this is just a way to define a metric on CPN minus 1. Okay, so and of course we have the gauge symmetry of doing a gauge transformation here and shifting alpha. And of course here we also have the term that we also had for the sphere of the sum over all CJs minus 1. So the physics of this term is exactly the same as what we discussed before. So we will generate a mass gap and all that story we discussed before. So first analysis we set A equal to 0, and oh sorry, I forgot one thing. We now do the same thing we did before. We integrate out the C's, right? We get an effective action for sigma tilde and A. Okay. To analyze this action, first we set A to 0. And so the action we get will be identical to the one we get for sigma tilde. Is the same as the one we get for the sphere. It has the same features. We have again the dynamical mass generation and so on. And now we check whether it was reasonable to set A to 0. So we'll consider the small fluctuations for A and try to see what happens when you have small fluctuations for A. Okay. And so when we consider the small fluctuations for A, so we'll have the A, and then we'll have full dressed propagators. So just the propagators, these are just simply free field propagators for C, but with mass m, which is that one. So all the strong dynamics is just simply in the mass for the field C, okay, which started out being massless. Yeah.
What happens if you take nth power of the defining equation in your action? It seems like even if you take nth power of the defining equation in the action, classical physics doesn't seem to change, but it seems like quantum physics could be largely different. For example, if you take n power of sigma of C, the absolute value of it at minus 1, then the classical solution should be saying that quantum physics could see
Yeah, so you could put the power of alpha here, right? But then this would be, this sigma, this might be a dumb way to write the action, okay? So you would write to introduce here other variables in such a way that you make this C quadratic so that you can integrate it out. And you expect the physics to be similar. So in this particular case you are asking about, I think I would expect the physics to be somewhat similar. Maybe if you choose this power too high, then the constraint might become too soft, and then you might have effectively more field. So it might be different. So you can analyze all these cases. So I don't know exactly what happens. So you can analyze it, but you will always use this technique. So you can analyze it using, I cannot tell you what the exact answer will be, but I can tell you that you can analyze it using similar techniques.
But isn't it kind of peculiar if the classical physics is same, but the quantum physics is different?
No, I mean this is common, right? So many times we have Lagrangians which are such that that classical physics is the same, quantum physics might be different. Yeah. Okay, so we have this diagram, and of course we have this diagram. Okay, and so this defines the propagator for A alpha, A beta, and let's say in momentum space Q minus Q. So basically what for an ordinary gauge theory would be the vacuum polarization diagrams, in this case just define the full sort of action for the gauge field A. And due to gauge invariance, in this action, so here there are vertices with derivatives and so on, and you are guaranteed that you will be able to pull out factors of Q of this kind due to the fact that that we have gauge symmetry. And now we can take Q to 0, very small, so we keep these factors of Q, and in the rest of the diagram we just set Q equal to 0, and so then the rest of the diagrams look like dk squared over k squared plus m squared, okay, squared. So that's essentially this diagram after we pulled out some factors of Q here and also combined it with this diagram. So this is familiar expressions for vacuum polarization of, let's say, gauge theories. But here, that's just the full action for this gauge field. And the important point is that we see that this action is essentially the Maxwell, this is the Maxwell kinetic term in momentum space. Okay? Of course, that's also familiar from vacuum polarization because vacuum polarization diagrams just renormalize the, let's say, electric charge, for example, and they do that because they have this particular form. Then now this combination here, well, I did forget the factor of n, so there is a factor of n here from the index loop here. And so the final action for the gauge fields will be something which, when we go back to position space, will have a factor of n, and then dividing an m squared. So the m squared came from just doing dimensional analysis of this integral. There are 2 powers of k in the numerator and 4 powers of k in the denominator. So we get this, and then we get f squared, where f is the field strength of the gauge field A. Okay. So A started out as a kind of Lagrange multiplier. The fact that we called it a gauge field was just some name that we had for it, but it's just some vector field that we integrated out in order to remove some that phase from the action. But then when we go to the infrared dynamics, we see that we end up with an ordinary gauge field which is weakly coupled. So for large n, this gauge field is weakly coupled. So it's that means that the physics of this model is that when we go to low energies, we'll have a bunch of particles on a line. Let's say we can have a C particle, we can have another C particle, or let's say a C bar particle J, let's say, for example. And these particles, if we didn't have the gauge field and we had the sphere model, well, okay, they move freely at long distances because the theory is capped, remember. But now, because of this term, there will be a force between these particles. And in fact, it's a force that grows with distance, with a small coefficient because the coupling is small, but nevertheless grows with distance. And so these particles will form a bunch of bound states and so on that you could go on and analyze. Okay. So to lead in order in n, you can neglect this interaction because the coefficient is small, but at long distances you cannot neglect it, and it leads to a new long distance effect. But the important point I wanted to point out is that we have an emergent gauge field. So we started with a theory which in the UV did not have a gauge symmetry. It was just an ordinary sigma model. So it's a two-dimensional theory whose target space is CP1, CPN. Okay, so a bunch of fields moving on this manifold, and at low energies we have a gauge field. Okay. Okay. In this case, it's just a U1 gauge field that couples to the overall. So these particles carry, let's say, charge +1, and these carry charge -1. Okay, so how am I doing with time? Okay.
So they form mesons, right?
Yeah, they form mesons. Yeah.
Can we study the scattering of these mesons?
Yes, you can study them.
Did people compute it?
I think there were papers discussing this, but I don't know. Yeah, sorry. The question is, can you study this? And indeed, you can analyze this. And he was asking me for references where it was done in the literature or not. I suspect it was done because it sounds like a reasonably simple problem, but I haven't read these papers. Okay. Okay, so now I want to discuss another example. So we had emergent gauge fields, and you probably saw some other examples of emergent gauge fields during these lectures. For example, did you have talks on, for example, four-dimensional Seibert dualities and things like this? Yeah. So that's an example where you start from some gauge theory in the ultraviolet and you get a different gauge theory in the infrared, right? So those gauge fields that you have in the infrared are emergent gauge fields. Now you might be confused. You might say, how could it be? I mean, aren't gauge fields fundamental and so on? And you probably heard many times. If Nati was here, he told you many times that gauge fields are not fundamental and so on. This is a very simple example where you see that you didn't have them in the basic description in the UV and you get them in the infrared. Okay. Now, I guess I would like to point one more thing out here, that something which is very important. When you have an emergent gauge symmetry, okay, the U1 that is gauged, in this case, is the U1 phase factor for these Cs, right, was not a symmetry of the UV theory, okay? It's not that we had a symmetry in the UV theory and then somehow there was some dynamics that generated the gauge field for that symmetry. It's very important when you have an emergent gauge field that there was no U1 symmetry in the UV. Okay, the UV theory had an SUN symmetry. Okay, but in particular it did not have a U1 symmetry. Okay, and the field theory in the infrared also does not have a U1 symmetry. Okay, there is this U1 gauge field, but it's a gauge symmetry. It's not a U1 symmetry. Okay, so there is no here. There is no global symmetry that shifts C by a phase. Okay. It's gauged. Okay, so that's also a general point. And so when we talk about emergent gauge fields or even emergent gravity, right? So we have, let's say, suppose we have a theory. We want to have a theory of emergent gravity. It's not that you start with a theory that has, let's say, translation symmetry and so on, and without gravity, and then you will get gravity out of the interactions, the graviton out of the interaction. So this has been shown not to be possible. And in some sense, the fields that are charged under the gauge, it's important that the full UV theory does not have as global symmetries the things that are going to be gauged once you introduce the gauge fields. So for example, translations are gauged in the theory of gravity. So you're not going to start with a theory which had in the UV had translation symmetry and then you are going to get gravity. So that's not going to happen. Okay. So now we'll discuss the Gros-Neve with some model which is I think it's a variant of the Gros-Neve model, but it's a model with fermions in 2 dimensions, and that displays an interesting phenomenon similar to the phenomena we've discussed so far. Okay, so the model that I'm going to write down will look a little funny, and I'm only writing it down this way to connect it to something we'll talk about later. Okay, so it's a model in d equal to 2, so now we are in d equal to 2 again. So it has left and right moving fermions, so which transform with some un indices. So we have left moving fermions, psi left I, okay. This transform under fundamental of SUN, this under the anti-fundamental of SUN. Similar for the right moving fermions, except that we want to put the index in the other position. So this is the only thing that is a little weird from what I'm doing here. And then we have some interaction, which is a 4-fermion interaction. Psi left I, psi right I. So the reason I put the index in a different position here is just to be able to write down this interaction. Psi left J, psi bar J right. Okay. So this is a 2-dimensional theory with a fermion that has dimension 1/2. So this has dimension 1. We are in 2 dimensions. So the fermion has dimension 1/2. And so this interaction here has 4 fermions, so it's dimension 2. This coupling is classically marginal. Okay. The quantum theory again develops a beta function, familiar story from what we discussed. And here again we can rewrite this this term. So now this full term we shall simply rewrite it as phi psi I L psi right I plus phi bar, well maybe I'll call this bar and this number, psi bar I okay. So and I forgot one term, plus or minus, which is plus 1 over g squared phi squared. Okay. So we introduced the new scalar field, and integrating out the scalar field, we get this interaction. And I think now you see where we're going. So can you guess what happens with phi? So there will be an effective action for phi, and the effective action is, well, we say we take a translation symmetry, so phi will be, again there will be a classical action for phi with an overall n in front. We take a phi which is constant, and then the part that involves the determinant will be the determinant of a fermion operator with some masses, right? Some of diagonal terms, some masses. So that's roughly the same as the bosonic determinants we were considering before. And so the equations will be essentially the same. And we'll find that phi, which is also the mass of the fermions, will get a vev which is of the order of e to the minus the sum constant divided by chi square n. Okay, so this is the same as what we discussed before. Of course, we have to choose the appropriate sign for chi squared and so on. That corresponds to attractive interactions between those fermions. Okay, so the interesting point here is that phi was a complex field because these operators were complex. I mean, this theory had a symmetry and an overall phase rotation of these fermions. So that's there is an overall U1 global symmetry. So there is a U1 of that rotates psi by e to the I alpha, psi r by e to the I alpha, right? And that symmetry is broken by the vev of phi. Now phi has charge 2, so the charge of phi. So if psi has charge +1, then phi has charge +2. Okay. So we break the U1 symmetry by choosing this vev. So there's a spontaneous breaking of the U1 symmetry. And we have now a massless mode, at least to lead in order in the 1/n expansion, we have a massless mode for this phi. Okay, so at very low energies, we will have this massless mode for the phi, a Goldstone boson. Now, as you probably know, there are no Goldstone bosons in 2 dimensions, and that those SNs discussion shows that that symmetry is restored. In this case, if you consider 1/n corrections, then again the phi will also generate some small mass. Some will be will be a scalar on a circle, and its vev will not be fixed, and so the symmetry will be restored again. But here I wanted to point out the behavior of these fermions. Now I'd like to make a few remarks about the similarity between this theory and the ECS theory of superconductivity. and how we have a kind of, let's say, we could call it perhaps accidental Larsen limit in those situations. So I won't discuss the BCS theory of superconductivity in great detail. I think a good reference for high-energy theorists is a set of lecture notes that Joe Polchinski gave in 1992. So, if you want more details, the lectures are called Fermi liquid, the effective field theory of the Fermi surface, or something like this. There are also some papers by Shankar, which discusses also similar things, with coming more from a condensed matter point of view. Okay, so if you have a Fermi liquid in so a bunch of free fermions in any number of dimensions, then you fill all the Fermi levels. So if you have a band, the structure might be a little more complicated. Let's say in flat space it would be a sphere, but in a band would be more complicated. But you will have a Fermi surface, and everything that is within everything that has energy less than the chemical potential will be filled. Okay, and then you can have the crucial point is that you can have very low energy excitations. So E minus mu can be small when you put a fermion very close to the Fermi surface, and you can expand the dispersion relation around the Fermi surface, and it will have an expansion of the form the Fermi velocity times L, where L is essentially the direction of the momentum perpendicular to the Fermi surface, okay, measured from the Fermi surface. Okay, so for a sphere, L will be the modulus of modulus of k minus k Fermi. Okay. Okay, so you see that if we look at the direction perpendicular to the Fermi surface, we have a dispersion relation which is linear in the momentum. That's exactly the same as what we have for a two-dimensional chiral fermion, right? So we have a dispersion relation which is linear in the momentum. So along each direction of the Fermi surface, we have, roughly speaking, a two-dimensional chiral fermion. Okay? And we have a different one for each point in the Fermi surface. Okay, now, so that's the free theory. Then you can consider interactions. Now, so in principle, you could have some interaction between four fermions, any four of these fermions, which could have, which could have any momenta, right? So we could have any momenta within this Fermi surface. But we're going to be interested in interactions that are relevant for low energies. And so since the low energy theory involves only the fermions that are on a thin shell around the Fermi surface, only terms that involve those momenta will be relevant. Okay, and so whatever interaction, so if you have some initial particle with this momentum and some, let's say, two initial particles with this momentum that scatter into other particles with some final momenta, both initial and final momenta have to be close to the Fermi surface. And that together with momentum and energy conservation impose some very drastic constraints. So if you require them to be exactly on the Fermi surface, then there are two solutions. One is that the two initial particles have very close momenta, and so it's essentially like a forward scattering. And the other possibility is that the particles that are scattering have exactly opposite momenta. Okay? So you have interaction that involves, let's say, the destruction of two particles with opposite momenta and the creation of two particles with exactly opposite momenta. And so this arises from some kinematics of the Fermi surface, right? And the details of momentum conservation. So in the end, you have this type of interactions. And now how this, of course, in the theory of BCS, this interaction between fermions was generated by integrating out bosons. And these bosons had essentially large frequencies for or large energies for the momentum transfers involved in these interactions. So you can integrate them out, and in the end you have this 4 fermion interaction. So, but now that we have just this type of interactions, then we can see that we get something vaguely similar to what we have here, in the sense that we have a fermion here that looks a bit like a chiral fermion, right? Interacting with another fermion here on the other side. And those are then also interacting with this one. So if we think of the position, the angular position on the Fermi surface as this index I, right? And here left and right, whether it's one fermion or the antipodal one, or maybe it could also be the spin up or spin down fermion. So if you think of them in this way, then you see that you get a model similar to that one. And those are interacting with a fermion which is in another point of the Fermi surface. That would be this other index j that we have here. Okay? So you see you have something rather similar, and then in that case the analysis of this model essentially then is similar to the analysis of this model, which leads to this massless particle, which is the Cooper pairs and the thing that breaks the U1 symmetry. So U1 symmetry in the case of superconductor is the U1 of electromagnetism. So that symmetry is then gauge, but for the purposes of this of BCS theory, you should think of it as a global symmetry. Okay. And again, there is a generation of a mass gap for the fermions, and this mass gap is exponentially small. Again, the interaction is marginal, and you have an asymptotically free theory. Okay, so my point so here the details of the analysis are not equal to the model, so there is not a precise duality between BCS theory and that model. I just wanted to point out some similarities. It's not exactly the same, and this model is a bit different because of the details of momentum conservation. But the point that is important is that you have the diagrams of this theory again are simple because of they have a structure similar to the structure you have in large N theories. So only bubble diagrams contribute and things like this. And all these bubbles together are essentially forming the kinetic terms for the phi particle, so the Cooper pair. Perhaps something that I didn't mention, but of course I should have mentioned, is this field phi gets a wave, and then you can expand this action around the minimum, and the phi will also get a propagator, so a kinetic term. So phi will be really a propagating field in this theory. And of course the same thing happens here in the BCS theory. And so I find it interesting that the Fermi surface in some sense has a large N already built in the sense that you have all these directions of momentum space that give you a natural large N. So people sometimes say, oh well, in condensed matter you never have a large N, or you have N equal to 1. Especially when we do ADS-CFT, we always apply to condensed matter, we always have to apologize for the large N. Okay? But BCS didn't have to apologize, they actually used the large N. So it might be that there are some clever ways to use the large N also for the SYK context. And people are actually doing that. Now I should point out that before, so if you're just told that, well, you have some theory of fermions or free fermions, and then you put some interactions, and the interactions are marginal, you have some running coupling that becomes strong in infrared, you say, well, it's going to be very difficult. You're not going to be able to solve it. So some strongly interacting fermions, okay, maybe you have superconductivity, but well, you can't solve it. And that's what people said. I mean, people really said this in before BCS. The Feynman, there are quotes of Feynman saying, okay, this theory is impossible. It's impossible to solve this. Or well, it wasn't referring to the phenomenon of superconductivity is impossible to solve. And now people are saying the same thing about high TC, so maybe there's a way to solve. Or they are saying the same thing about many things that we work on. And so just you should just have the right idea. But it's quite remarkable that that theory was solvable, and that there is such a simple solution. Okay, so I think I'm finishing here. So do you have any questions? Yeah.
Just a comment. The CPM minus case.
Yeah.
So in the volition IR, you mentioned that because A takes special value, so the matter field is heavy, so we go out the matter field, get that term.
Yeah.
But at the volition UV, I think we also have to mention that the C takes special, this square takes this to power 2 takes special value, so PG field heavy, we should integrate out. Go to nonlinear scale model, go symmetry. So this is even. But this theory right out is just a linear scale model. So I think the Gauss is still even. We have PG symmetry. We're dancing at one. So you get my point.
I don't think I understood, but I think what you're saying is that instead of defining this theory, we could have defined the linear sigma model. So if instead of doing this, we had put a square here and not.
You say the frame was in the SUN, there's more jump. You have to go to nonlinear sigma model. So go to the nonlinear sigma, you have to integrate out. You expand your field around the ground state, then integrate out the maximum mode. And you can see that we have both PG field.
Are you saying that this analysis was not done correctly?
It's correctly, but
Okay.
small jump, just small jump. Anyway.
Okay. Well, I'm afraid I didn't understand the comment, but.
More questions?
Yeah.
So in this case, the thermodynamic limit required for spontaneous asymmetry breaking is independent of the larger limit.
Well, I mean, so here you have to be careful. I was very qualitative here. I said the details are different. So I didn't tell you what the n was for the BCS theory. Okay. So, I mean, of course, if it was exactly equal, there wouldn't be symmetry breaking because there wasn't. And if n is finite, there isn't symmetry breaking. But in some sense here, the volume is infinite, and you should not. If you want the precise description, you should look at this paper, or even some condensed matter physics paper. This was just a qualitative discussion. But the basic idea is that the reason why there is a large n is basically the following: an effectively large n is that when we go to low energies, we are interested in Ks that are small, right? We're interested in energies that are small. Small compared to the Fermi energy, and that translates into momenta which are small compared to the Fermi energy. Okay, so we are interested in relatively small momenta here. Okay, so when we think about the low energy theory, we could imagine putting an infrared cutoff. So the UV cutoff of the low energy effective field theory could be relatively small here, smaller than K Fermi. Okay. This is the UV cutoff of the low energy theory, right? Of the low energy effective theory. So we're going to have a low energy effective theory where basically we could define a bunch of cells here which have we put some momentum, let's say K lambda. This momentum K is the UV cutoff for the infrared theory of the infrared effective field theory. In the same way that when we think about the Fermi theory for weak interactions, right? That theory we pick a UV cutoff which is much smaller than the mass of the W, right? So here we're going to pick a cutoff for the low energy effective theory much smaller than the Fermi energy. Okay. And when we do that, then there are many of these cells, right? And that's basically the large n.